Okay, hello, good morning, everybody. Welcome to the second day of our conference. We start our morning or afternoon or very early morning session, depending on the time zone you are in. The first speaker of the session is Anna Miriam Benini from Università of Parma, and she will tell us about dynamics of transcendental Henon maps. And please notice that the talk is generally 2 hours, but there will be a break, something about half after half of the talk. Okay.
So today will be a mini course about a specific type of map, F, which goes from C2 to C2. And our map will have the special form f of zw, so z and w are the two coordinates in C2, equals f of z plus minus delta w comma z. And f is an entire transcendental function from the complex plane into itself. So this is really an analog, a transcendental analog of the so-called Henon maps, which have been studied a lot, in which your F, instead of being a transcendental entire map, is just a polynomial. Okay, and in the case of polynomial, they've been studied so much, partly because there is a result by Friedland and Milner, which tells you that all polynomial automorphisms with interesting dynamics. I will define automorphisms in a second. So there is a big theorem by Friedland and Milner, which implies that all polynomial automorphisms with interesting dynamics can be written as a finite composition of Henon maps, okay? Normal Henon maps. I will call them polynomial Henon maps, but people just call them Henon maps. And another important features of these polynomial Henon maps, which have been studied so much, is that you can use some techniques from one complex variable to study some of their dynamical behaviors. So in our case, the main reason why we try to study this transcendental Henon maps is because you can use a lot of techniques from one-dimensional dynamics in order to deduce properties of these maps. So these are automorphisms of C2, which means that they are injective and surjective. So this is a completely different, they are degree 1 from the topological point of view. This is completely different from what we have in one variable, in which transcendental maps have infinite degree in the topological sense. So in C, you take a transcendental map, and every point except at most one exceptional point has infinitely many preimages. In C2, in this specific class of maps, every point has one and exactly one preimage. So in particular, for example, the blow-up principle that was talked about yesterday in the talk about storage map does not work. Okay, so every point just has one image and one preimage. So there is no way that you can have a neighborhood which expands and covers the entire space. Let me tell you 1 second how another advantage. So what are the advantages of transcendental Henon maps? One is that this special form allows you to use one-dimensional techniques. Well, and second, the fact that it's an automorphism allows you to use the techniques from R2 diffeomorphism, which some of you may know, some of you may not, but there are a lot of results about existence of stable and unstable manifolds. There are many results which work for diffeomorphisms of R2, and you can use several of these results for your maps from C2 to C2. Now, what is the structure of this talk? I will do some very basic session in which I will mainly discuss periodic points for these maps. And then I will give some presentation with Beamer about Fatou components for automorphisms of C2. And finally, I will show you how to construct a Baker domain for some type of maps of this family. And so the first, I will make a break around here, which will be a bit after half of the talk, okay? So the last part will be a bit shorter. Of course, construct just means telling you more or less how you do it, of course, without details. So the first observation is that these maps have constant Jacobian. What is the Jacobian? So you have your map, which is here, okay? F of z w is equal to f of z minus delta w comma z. And its differential is a 2x2 matrix, which clearly depends on the points where you compute it. So this is, you compute it, and it's f prime of z, 1 minus delta 0. When you take the modulus of this matrix, so the modulus df, it becomes constant. This is just delta, okay? So the modulus of the, well, you often indicated by the modulus of the differential and or the determinant as you like. You just do your computation and it just turns out that it's delta. So it's always constant, which basically tells you that constant in the sense that it's independent of the point in which you compute this determinant. So this really tells you several things. It tells you, for example, that you cannot have at the same time repelling and attracting points, okay? Because this modulus of this Jacobian, this modulus of the differential, really tells you morally whether your map is locally expanding or contracting or volume preserving. So this is one of the properties that you cannot have simultaneously for one specific map. There is no coexistence of repelling and attracting points, periodic points. And another thing which is really interesting is that this differential has two eigenvalues, okay? And the product of these two eigenvalues is delta. So what this is telling you is that if one direction is very expanding, so one of these two eigenvalues is very large in modulus, then the other one needs to be very small. How small? Depending on delta. But somehow this tells you that if you can find points or sets on which one of the two directions is very expanding, automatically the other direction will be very contracting, okay? This can be used in several different situations. Now, there is something else which is a bit, so this is, I will write, if one direction is very expanding, the other is very contracting. Okay, now another observation, okay, that for the people in one variable. It's if you compose Henon maps, if you compose transcendental Henon maps, they are not invariant angular composition. So the composition of two Henon maps is not a Henon map. So the composition, I will just call them THM, okay, which is a very luck-bringing name for a class of maps. So a composition of transcendental Henon map is not a transcendental Henon map. Okay, so the very first thing that I would like to look at are periodic points. We all know the definition of periodic points. So a point P, Z0 with coordinates Z0, W0 is periodic of period K and usually you take the smallest k for which this happens. If f to the k, this is the composition of f and k times, okay, but we're all dynamicists, so this should be clear, of your point P is equal to P. This is just the same definition that we have in one variable, and there is nothing mysterious about it. So in one variable, you classify periodic points according to the multiplier. What is the multiplier? If k is your period, their multiplier is the derivative of f to the k prime calculated in your point. Okay, and you have basically, let's call it lambda, and you have basically three cases with some subcases. So if the modulus of lambda is bigger than 1, then your point is repelling. If your modulus of lambda is smaller than 1, your point is attracting or super attracting. I don't want to get into this. If your modulus of lambda is equal to 1, you have several subcases. If it's linearizable, it's the center of a Siegel disk. If it's not linearizable with an irrational rotation number, it's a Kramer point. I'm not going into this because I think you all know it. And if it's a root of the unity, it's parabolic. So in 2D, there is no point in looking at the modulus. Of course, you will look again at the differential of f to the k computed at your point P, but there is no point in looking at the modulus of this differential just because we just saw it's a constant. By modulus, I mean the determinant, sorry. So there is just no point. What you look at are eigenvalues, okay? So if both, let's call them lambda 1 and lambda 2, and let's just say lambda 1 bigger than lambda 2 in modulus, just for simplicity of notation. Well, you don't need it. Let's call them just lambda 1 and lambda 2. Then if they are both in modulus bigger than 1, your point is called repelling, nothing new. If they're both in modulus smaller than 1, the point is called attracting. Again, so far nothing new. And an interesting case that does not appear in one variable is when one of them has modulus bigger than 1, and the other one has modulus smaller than 1, and this is called a saddle point. All these three, for people who know, all these 3 points are hyperbolic, okay? In the case that one of them is modulus equal than 1, you can have, again, several cases. And it's actually much more complicated than in one variable, so I'm not going to get into this. But you could have a semi-attracting case if the other one, well, a semi-repelling case if the other one has modulus bigger than 1, semi-attracting if the other has modulus smaller than 1. And if the other one has modulus equals to 1, there is a lot of possibilities. There are something called resonances. There is a whole local theory based about what happens when both have modulus equal to 1, okay? So this is a mess, at least from my perspective. For all of these cases, you have some local theory. I'm not gonna get into this because at the moment, we don't even know that periodic points exist. So let us try to see if periodic points exist for our transcendental Henon maps and what type of periodic points and under which assumptions. But first of all, let me do one more remark. So when you are in C, a periodic point satisfies the equation f to the k of z minus z is equal to 0. Okay, so if f is a transcendental function of degree of is really a transcendental function, the solutions of this equation are discrete. So periodic points of any period are discrete. When you look at maps from C2 to C2, this is no longer obvious. They could form complex curves, okay? Now, one of the first things that you can prove, it's a fact. I'm not going to give you the proof. So fact, if F is a transcendental Henon map. So do you remember transcendental Henon map? F of z, big F of zw is equal F of z, small f of z, entire transcendental function, minus delta w, a linear perturbation in w, comma z, okay? I'm gonna remark, so transcendental Henon map, so f of zw is equal to f of z minus delta w, comma z, with your f, which has low order of growth, less than 1/2, I think, less or equal than 1/2. Then the periodic points of every period are a discrete set. But this is not obvious in general. Maybe it's true, we don't know. Okay, now let us take a closer look at periodic points of period 1 and 2. Let me first remark a little bit about the special form of this map, okay, just so that we can keep it in mind while we discuss our properties. So f of z w equals f of z minus delta w, comma z. You can see it. It's a possible way of seeing it. It's not the only one, but you can see it as in the first coordinate, you have a one-dimensional dynamics in which your z maps to f of z, small f of z, with a linear perturbation term in the second coordinate. So if at the first step, if your w is very small, this is basically the one-dimensional dynamics, but just at the first step, because at the second step, the new perturbation term will be given by the new w term, which is just your z, okay? So you have to be very careful when you think about it as a perturbation term. It's just true for one step. And the second observation is that your new w is really the previous z. So this is kind of a swap in the coordinates in a certain sense. Again, valid at the first step, because at the next step, so this will be the new z that you plug in, so with your perturb term, and the new perturbation term will be this z. Okay, but at a single step, you can see this is a one-dimensional dynamics with a linear perturbation, and then the second coordinate is just a swap, just becomes the old first coordinate. Now let us take a look at fixed points. So periodic points of period 1 and 2. Well, we all know that periodic points of period 1, we usually call them fixed points. And now let's look at the explicit form of our map. What does it mean for a point f of zw to be equal to zw? It means, what is f of z? It means that this should be equal to f of z minus delta w, comma z. So this tells you immediately that it needs to satisfy the following two equations: f of z minus delta w equals z, and z equals w. You substitute, and you get that f of z minus delta z is equal to z. Okay? So this is true if and only if f of z minus delta plus 1 z is equal to 0. So this is really an equation in one variable, so solutions are discrete. and they exist unless this function, let me call it h of z, is of the form e to the h tilde of z. So the solutions of this equation, it's a bit slow in charging when I write. So the solutions of this equation that I just boxed in pink are exactly the zeros of this function f minus delta plus 1, the identity. So this function has zeros unless it is of the form e to the some other entire function. Or if you want, if delta is different from -1, if z is a fixed point for the function g equals f of z over delta plus 1. Okay, so so fixed points exist in many cases, and they will be points of the form fixed point of f equals the set of points. They are on the diagonal, so they are of the form zz in C2, where z is a fixed point for this function g. And again, we know that, I don't know what this, I don't know, there is a new, whatever. So we know that there are entire functions without fixed points, so, but there are not many, so unless g is of the special form of entire functions without fixed points, which basically goes back to this representation of entire function without zeros, then you have fixed points, but not in general for every transcendental Henon maps. So you may wonder now, what happens if you're, what happens for period 2? Suppose that, so in many cases, this is telling you that in many cases that you can precisely characterize your transcendental Henon maps as fixed point, but not in every case. So does it always have periodic points of period 2? Notice that with this, well, so what about period 2? This time you need to be a little more careful when you write down your equation. You do the same trick. So you consider a point z naught w naught. This goes to the point f of z naught minus delta w naught comma z naught. And then you apply your map again. It's actually, there is a little trick here. It's better to consider the inverse map, but we're not going to get into this. What you get is that periodic points of period 2 satisfy the equations f of z equals 1 plus delta w, and f of w equals 1 plus delta z. And then, so you can do it in this way. Either you reapply your function again and then use a little trick of changing variables, or instead, or you remember that your function is an automorphism, so you consider the pre-image of this point, and then you get these two equations. Anyway, so if you remember that function g, so if delta is different from -1, so this is a necessary hypothesis, what you get is that, no, sorry, when delta is equal to -1, who are the solutions? Your equation just become f of z equals 0 and f of w equals 0. So the periodic points of period 2 for your big function f, for your Henon map, are just the set of pairs zw in C2, such that both z and w are zeros for f. again, this is a bit of a problem because your function f may not have zeros. Okay, we go back to the previous problem that we had before. So let me recall you that f may not have zeros. If f, this time, not the other function that we wrote before, but truly f is of the form e to the sum entire function. Okay, so in this specific case, it may not have, in fact, it will not have periodic points of period 2. What happens in the other case, in which delta is different from -1? You divide by 1 plus delta, and if you write g of z as f of z divided by 1 plus delta, then what you get is that this system becomes g squared of w equals w and g squared of z equals z. I hope I didn't make a mistake here. Let me check. So if you have so this just sorry, I just need to make the computation for my own peace of mind because I'm getting a bit confused. So this becomes f of z over 1 plus delta. We clearly need is equal to w. And now I apply the other one is f of w over 1 plus delta is equal to z. So I plug this w in and I get that this becomes g squared of z. Okay, so this is okay. Did you see what I did? It's simply just w. This is the pens are always a bit tricky. So this w is just g of z. So I plug this in again and I get these two equations, g squared of w equal w and g squared of z equals z. So the set of periodic points of period 2 for f are the set of points of the form z g of z, where z is a periodic point of period 2 for g. And now you will complain. So what did we gain with respect to points of period 1? Well, now we have a theorem by Bergweiler. I think actually the part of existence was already due by Baker, which tells you that if G is it's a transcendental entire function from C to C, then for every period n bigger or equal than 2, G has infinitely many points of period n, and which is interesting for us, you will see in a second, their multiplier goes to infinity. So what does this tell you in our case? That in this case, so what was the assumption? The assumption was delta. So we had two cases, okay? If delta is equal to -1, you have periodic points of period 2 if and only if your function f has zeros, small f has zeros. If your delta is different from -1, you basically reconduce yourself to looking at periodic points of period 2 for an entire function from C to C. And at this point, you have a theorem which tells you that such periodic points always exist. So in this case, if delta is different from -1, periodic points of period 2 for your big F always exist. And from the fact that the multiplier goes to zero, sorry, the multiplier goes to infinity, you can compute df squared at your point p periodic, and when the multiplier in the one variable goes to infinity, you will find that this becomes a hyperbolic point, a saddle point, as we defined before. So, and there are infinitely many of them. All the ones who reach the one variable point have sufficiently big multiplier, which are actually saddle points. So why do we care about saddle points? Well, there are many reasons why we care about saddle points. One of the reasons is that there is a very well understood local dynamics at saddle points. But another point is that I did not define it, and I'm not going to define it today. But this implies that if delta is different from -1, the Julia set is non-empty. So there is a bit of a mess in defining the Julia set in several complex variables for several reasons, and I don't want to get into this. You can think about it as usual, the set of points near which the iterates are normal. And now there is already some problems because your function is really an automorphism. So when you look at the dynamics of differences in R2, everything is symmetric when you go forward and backwards. So there is already something to discuss here about whether it's correct to look at the forward iterates rather than at the backward iterates, or the intersection of the two, okay? So, but for us, the Fatou set will be the set of points, the Fatou set will be the set of points for which the forward iterates are normal. And there is also another issue about normality, that normality really makes sense when you go from a neighborhood of a point to a compact space. And while we all agree that the correct compactification for dynamics in C is the Riemann sphere, there is a bit of arbitrarity when you go to C2, okay? We will take as compactification the complex projective space. I'm gonna tell you what you need to know about the complex projective space in case you're not familiar with it. But for now, let me just tell you that however you define the Julia set in a reasonable way, what you get is that the Julia set is different from zero because several points are in the Julia set. Now, what about the functions that we left behind? What about the ones with delta equals -1? In fact, you can do more. In fact, the Julia set is always different from the empty set for every f. And you can prove this in a completely different way. You can prove this in a very different way. So how can you do this? I'm just going to mention it because it was mentioned in the talk by Gwyneth Stallard about this beautiful construction by Eremenko about constructing escaping points. So what you can do is that, so it goes in 2 steps, okay? Let me remark something. When you have points of period 1 and period 2, you can study their multiplier and you can study their differential and deduce properties about it. So when you have what is the only case left which has no periodic point? It is the case in which delta is equal to -1 and you had this function had a special form that we saw here. This is of this special form. I'm not going to write it down. So even in this case, when delta is equal to -1 plus and there are no periodic points of period 1, no fixed points, you can deduce by doing some tricks that there exist periodic points of period 4. And then you put this together by proving the following. Every transcendental Henon map has escaping points. So clearly a map which has fixed points and escaping points cannot, needs to have non-empty Julia set. Okay, so these two properties together imply that the Julia set is non-empty. Let me just mention that to prove that you have escaping points, you really use Yermenko construction. So there is this Riemann-Walleyron theory, which tells you that near appropriate points, you have small neighborhoods which get mapped over big annuli. And you basically then take your big annuli, find another good point, another small neighborhood gets mapped to another very big annuli, and so on. And in this way, by looking at inverse branches in the correct way, you can construct escaping points, which in one variable, you can prove they escape as fast as possible. So the same construction, you can apply it to transcendental Henon maps to construct orbits which go to infinity. And even more interestingly, each of these points which go to infinity is attached something which is called the stable manifold. You should imagine a copy of C, and these copies of C are mapped to one point to the next in the orbit, contracting towards the orbit of the point. So you can really use Yermenko construction, but the extra room that you have in C2, together with the fact that you have constant Jacobian, allow you to deduce that in fact it has this set of escaping points really has at least dimension instead. So in one variable, you find often, in many cases, rays of escaping points. In this case, in C2, for each escaping orbit constructed in this way, you find complex curves attached on which you can understand exactly how the orbits go to infinity. It's not unthinkable to imagine that with sufficient work, you can actually find curves in C2, and in each point, the analog of the rays, and in each point of these rays, you could attach complex curves, so you would get something of real dimension 3, morally speaking, on which the orbits go to infinity. Okay, parenthesis closed. What are other very strong properties that you can prove for transcendental Henon maps, which I think are interesting? And then we will move to a little bit of exploration of Fatou component, but let me just finish this. So another thing that is very interesting is that the Fatou set is pseudo-convex. Now, this may sound like not very interesting from the point of view of one variable, and I'm not even gonna define pseudo-convex, but this is something which is an important property from the geometric point of view, okay? It's kind of a notion of convexity, which is invariant under biholomorphism. So this is an important property. I'm wondering whether this has consequences. We haven't explored this yet. And I forgot something super important. This is most of the, let me write it in red. So most of what I'm telling you today is joint work with Leandro Arosio, John-Eric Fornes, and Han Peters. Oh, sorry, Han. Well, you're present, so you deserve your name to be written, but let me just be homogeneous. And Han Peters. And the very last part is joint work with Saracco, Alberto Saracco, and Michele Azzetta. Okay, so it's mostly with the red people, but the last part is with the pink ones. So another property which is very important from the geometric point of view is the Fatou set is pseudo-convex. And you can construct several types of wandering domains. And here there is a lot to say, but I'm not gonna get into this. And finally, let me not be precise here, but there is some reminiscence of the essential singularity at infinity. I don't want to be precise here. Now, the last thing that I want to tell you about is about the complex projective space. If you know what it is, fantastic. If you don't know what it is, this is what you need to know. People usually draw it like this. This is C2, and this is the line at infinity. So the complex projective space is equal to C2 union a line at infinity, which is really biholomorphic to the Riemann sphere. This is called the line at infinity. And it's the one that I'm drawing in pink here. Okay, and what you need to know is that points in the line at infinity are identified by 3 coordinates. This is the complex projective notation, P, Q dots Q, 2 dots 0, and that a sequence of points Pn in C2, whose norm goes to infinity, is said to converge to a point P, Q, 0 in the line at infinity, if and only if the ratio of its coordinates converges to P over Q. So this is the point ZNWN. This is a honest point in C2. And it's this sequence of points. This is not an orbit, okay? This is just points. This is just a geometric, I'm just trying to explain you who are points in the line at infinity. So if you take a sequence of points, not an orbit, just a sequence of points which converges to infinity to the boundary of C2, then we say that they converge to a point PQ0 on the line at infinity, if and only if the ratio between the first and the second coordinate converges to P over Q, okay? So for example, if the modulus of Zn over the modulus of Wn converges to infinity, then your points Zn, Wn converge to P over Q with modulus of P over modulus of Q, which goes to infinity. So they converge to the point infinity 0, 0, which is not the correct way of writing it. What people do is to write 1, 0, 0. So the ratio of modulus of Zn over modulus of Wn converges to infinity, which is exactly equal to, say, 1 over 0. Okay, so this is your point 1, 0, 0, which essentially corresponds to the point infinity in the Riemann sphere, because your line at infinity is really a Riemann sphere. And this will be the point 0, 1, 0, in which the ratio between the ratio between Zn and Wn in modulus goes to 0. If the 2 points go to 0 approximately equally, then you will converge to the point 1, 1, 0. This is all you need to know about the complex projective space. Okay, this is a direction of line. This is basically indicates the directions in which your points converge to infinity. So I will do a break, but not now. Let me first do some work about Fatou components in C2. So if you have questions about it, maybe it's a good time to ask, but the break will be in about 20 to 30 minutes. So we will be a bit late with the break, okay? If there are no strong objections. Questions?
I have one question.
Yes. Hi.
Yeah. Hello. Yeah. It's regarding the beginning. You mentioned that composition of transcendental Henon maps is not a Henon map.
Yes.
Right? And my question is it always true like that, or under certain conditions that it is not? And if it is under certain conditions, has any work been done in this direction?
So I think it's in general not, because your function f is not linear. So I think it's in general not true. But you can still say a lot on the dynamics. I don't want to say something stupid. Okay, I will need to check. But I think it's in general not true, because in the second step you get at the very second step, in the second coordinate, you get f of z minus delta w, which is never the previous coordinate.
Yeah. Can it be under certain conditions? So putting some conditions on these functions.
Maybe. I'm not. I don't think. But maybe maybe it's like this. I would need to check. Maybe after the talk we can sit down 5 minutes and check. I think it's not possible, but we should check.
Okay. Thank you.
Okay. So let me discuss a little bit about Fatou components. So So let me see. Okay, fantastic. So we will look a little bit about known results about Fatou components in 1 and 2 variables, and then I will present you some construction of Baker domains, which are kind of a new type of Fatou components in 2 variables, and then I will give a little bit more details about one of these possible constructions. So what are the classes? This is kind of a panoramic view of Fatou components, and I wanted to give a view of Fatou components for automorphisms of C2, but since the audience is in 1 variable, I will give a parallel with what we know about Fatou components in 1 variable. So what are the maps that we are going to consider? No poles, okay? No rational maps, no Hermann rings, no meromorphic maps. Polynomials and transcendental entire maps in 1 variable. Polynomial automorphism, more precisely, polynomial Henon maps, which have the specific form we talked about before, and transcendental Henon maps in C2. These are the maps that we will do. And you see they really form a table. Polynomial in C and polynomial in C2, transcendental maps in C and transcendental maps in C2. They're all automorphisms, the one in C2 for now. So some very basic dichotomy. We are used to think about the first dichotomy being the Julia set versus the Fatou set. But even before getting into this, another dichotomy is whether your orbits basically accumulate in the manifold that you're considering. Our manifolds are M equals C or C2, okay? I just wrote M so that I don't need to write both C and C2 every time. So we take our maps, which as we said, are polynomials or entire maps in C, or Henon maps, transcendental of polynomial in C2, and we look at the iterates. The very first dichotomy, and many people, like for example, Rippon and Salar and many others, Rempe, Schleicher, many of the people who talked yesterday actually worked a lot on the escaping set in their career. And in fact, it's a very basic dichotomy. What do orbits do? Do they converge to the boundary or do they accumulate in compact sets? Okay, so our very first dichotomy for today is whether points are escaping, which means the orbit really converges to the boundary, or they're non-escaping. And let me tell you that, so we have in C, we all know the example of the standard function. So about the z goes to z squared. And in this case, we have the unit circle in which dynamics will be chaotic, but still the points will stay in the unit circle. They will not converge to infinity. Outside the closed unit disk, you will converge to infinity. Inside the unit disk, you will converge to 0. So really, your set of escaping points in this case is the complement of the closed unit disk, and we all know how to generalize it, how to describe precisely the set of escaping points in polynomial dynamics. In C2, let me just make you a simple example, because this is the example that we will take as a starting point for our construction of Baker domains. You look at this linear map from C2 to C2, okay, which sends ZW, it makes a swap. We need a swap because our Henon map, our basic Henon maps have a swap in the second coordinate, and you expand the first coordinate linearly by a factor 2, okay? So ZW goes to 2WZ. Clearly, every point escapes except the point 0, 0. Is it correct? Yes, sorry. As long as as soon as one of the two coordinates is non-zero, everything, the orbit will be escaping. The second basic dichotomy, which you all know about, is the Julia set, where, this is important, okay? So in case there is somebody who is not transcendental here, so in polynomial case, you either stay bounded or go to infinity. In the transcendental world, you can accumulate on the entire plane. So there is no dichotomy. You could stay bounded, go to infinity, have unbounded orbits. There are 3 different possibilities, and the 3 of them occur. Now, the second basic dichotomy is the usual dichotomy between the Fatou set and the Julia set. I'm now going to define normal family for you, because you all know better than me. And let me just remark it, really, normal families work well when your target space is compact. Our target space is C2, so we need to compactify it in some way. We choose the complex projective space. There is a long discussion about it, but this is what we chose. And the stable set is the set of points on which the iterates are normal in neighborhoods. And now let us look a little bit at what happens again in our 2 very basic example. So in the Z squared example, the Julia set is the unit circle. Why? because points in every neighborhood near the unit circle, you have points which go to infinity and points which go to 0. So there is no way that any limit function or subsequence of limit functions can be convergent. And the open unit disk and the exterior of the closed unit disk are both in the Fatou set. So in both cases, the functions converge to constant limit functions, okay? So in one variable, this is not very crucial, but in two variables, you start really having to look at what is the rank of your limit functions. We're going to get into this. And the other example, our linear example in C2, you compute the even iterates. So this is interesting, okay? You compute the even iterates and the odd iterates, and you get that the even iterates of, you see the hand? Yes. So the even iterates converge to the point on the line at infinity, ZW0, while the odd iterates converge to the point 2WZ0. So every point except for 0 is in the Fatou set, but even iterates converge to one point, which depends on ZW. So it's really a limit function which associates to the point ZW, the point in the line Z, W, 0, sorry, Z 2.W 2.0, and the odd iterates convert to a different function, the function in which the coordinates are reversed, and you even get a factor 2, okay? So this is kind of a bit weird from the one-dimensional perspective. You get two different limit functions, even in this very special linear example. What types of Fatou components can you have? We talked about it yesterday. They can be periodic, pre-periodic, or wandering. So long story about wandering domains. In C, polynomials do not have wandering domains. In C2, they do have wandering domains. For endomorphism, this was proven by Astor, Dujardin, Raisi, and Peters. I'm missing somebody. Buff, Astor, Buff, Dujardin, Raisi, and Peters for endomorphism, which are maps from C to C2, polynomial, but not automorphism, like we said in the beginning of this class. And what is very interesting about their example is that these wandering domains have bounded orbits, which in C is a big open question. Can you have entire transcendental maps in C with wandering domains whose orbits stay in a compact set? Nobody knows, okay? So I think this is very interesting, but as far as I understand their techniques in C2, there is no way to push it down to get something in C. And the second observation is that there are results, general results by Pierre Berger and I cannot recall the name right now, but by two recent authors who seem to apply very general techniques in parameter spaces to deduce that there must be polynomial automorphism with actual wandering domains. Okay, so Sebastian Bibler, thank you, Fabrizio, thank you so much. I knew you would be crucial here. Sorry. Okay, in this talk, we only talk about invariant Fatou components, okay? Not even periodic, they are invariant. So f of your Fatou component u is equal to u. And we will kind of keep an eye on escaping Fatou components. So what is an escaping invariant Fatou component? Is a Fatou component which is invariant, so it gets mapped into itself, and on which the iterates converge to the boundary of your domain of definition. In our case, the line at infinity. In the C case, in the one-dimensional case, they converge to the point at infinity, because in that case, the one-point compactification, there is no discussion about whether this is the right one. This is the right one, as far as we know for now. Okay, so what about invariant Fatou components for polynomials? I know you know this, but I want to put it from a slightly different perspective. So there is exactly one escaping Fatou component, exactly one component on which the orbits go to infinity, and it's a tracking basin of infinity. You all know how we construct it, okay? Basically, a polynomial in a sufficiently large radius will map this large radius, even this large disk, closer to infinity, and then you take pre-images. I mean, we all know how to construct a basin of infinity. The point is, for polynomial, there is one and only one escaping component, escaping invariant component. It contains a neighborhood of infinity, so there is no way another invariant escaping Fatou component can squeeze in. And then we have our user classification of invariant components, which are non-escaping. They can be attracting basin or super attracting basin. everything converges to a fixed point in the basin. They can be parabolic, everything converges to a fixed point on the boundary, or rotation domains. Your limit functions here are really rotations of some angle theta, okay? So your limit functions, we will see it, are of rank 1, not of rank 0 like in the other cases in which the limit functions are constant because they're really fixed points. And these are the pictures. Another thing that is very interesting here that I want to stress is that we have a normal form. So in the attracting basin, your function is conjugate to either z goes to lambda z or z goes to z to the d. In the parabolic basin, you're conjugated to the translation by 1, and in the rotation domain, you're conjugate to a rigid rotation on the unit disk. So what you can't really appreciate here, but I want still to mention, is that there are two factors here in the way we look at Fatou components. One is the geometric classification, which is very simple because in our case, when things are entire or polynomials, when things are polynomials, we didn't get to entire yet, all the Fatou components, except possibly for the basin of infinity, which could be infinitely connected, but all other Fatou components are disks. And even in the case of the basin of infinity, which may not be simply connected, the structure is very well understood, okay? And the other point of view is the dynamical classification. Once you have your set, you understand it geometrically, it's a disk, unless it's the basin of infinity. Then you want to understand what is dynamical behavior in it. How do you do it? You take model maps and you construct conjugacies. Okay, so let's keep these two factors in mind. Let us look quickly, well, some images of Fatou component. The black one is the basin of infinity. In this case, is multiply connected because the complement are these points which form a counter set. This is an attracting cycle of period 3. This is the parabolic basin, and this is a single disk. And this I took from the web, so I don't know whom to credit for it, okay? I took another image from the web that I will show you later on that I don't know whom to credit. Maybe it's still the one from Shrita, but I'm not sure. So what happens for transcendental function in C? All of a sudden, infinity becomes an essential singularity. So there is no longer an attracting basin of infinity. You have directions in which when you look at your point at infinity, you have directions in which you move closer to infinity and directions in which, by Picard's theorem, you move very close to 0. So there cannot be an attracting basin of infinity. Is it a bad news? No, it's a good one, because this opens up the possibility for other Fatou components to exist. And these Fatou components are called Baker domains. So what is the definition of Baker domain in one variable? There are several equivalent definitions. One that you can look at is a Baker domain is an escaping Fatou component, which is not an attracting basin. Now, the standard definition that you've probably seen is that a Baker domain is a periodic Fatou component on which the iterates converge to infinity, okay? But for now, what I would like to stress in this talk is that really, as soon as you're not an attracting basin for infinity, which implies you are a polynomial, then a Baker domain is an escaping Fatou component on which does not contain a neighborhood of infinity, which is not an attracting basin of infinity. And there is a nice classification of Baker domains, which tells you that every Baker domain is simply connected, biholomorphic. This is a bit tricky. To show that Baker domains are simply connected, there is no direct proof. There is an indirect proof in which Baker has shown that if you're multiply connected, you need to be a wandering domain, and even a wandering domain of a special type. Okay, so let me just say it's a bit interesting, I think, that I don't know, maybe you know of other proofs of the fact that Baker domains are simply connected in the entire case, but the only proof I know is an indirect consequence of a theorem by Baker, which tells you that if you're multiply connected, you are a wandering domain. Now, so then every Baker domain is biholomorphic to the disk or the right half plane, as you like, because they are all biholomorphic in C. As soon as they're simply connected, they are biholomorphic in C. So the geometry is done, okay? You are H, you are a disk. And it is conjugated to one of the following normal forms. Either multiplication by a factor with modulus bigger than 1, which you can turn it into a real number, or you're conjugated to a translation along the boundary. I'm going to show you a picture in a second, or you are conjugate to a translation transversal to the boundary. Let me show you a picture and then let me make a disclaimer. So basically, the possibility you have for Baker domains, the pictures with the disks are just if you want an alternative vision. But basically, your Baker domain, you can imagine it to be a right half plane on which either you move along the boundary in one direction or the other. These are conformally to different types of maps, or you can move away from the boundary. And here, I'm not 100% sure whether the Riemann map which brings you to H is also the Riemann, is also the map which conjugates you to this translation. I need to check, but I didn't find it yet. So this may be that it's true that in the second case, you're conjugate to a translation which is basically orthogonal from, which basically takes you away from the boundary, but I need to check if this is really the same map which makes you be holomorphic to the right half plane. And then the last possibility is the possibility in which you have kind of a source in the boundary and everything spreads out from this source through a multiplication by a real number. So notice that one may be really tempted at first to think at Baker domain in C as parabolic points in which a parabolic point moves to infinity. And notice that this classification really tells you that already in C, even before getting into the complicated problems that Lasserempe was talking about, that the relation between critical values and so on, even before getting into all these kind of problems, which are still being investigated today, you do have different dynamical behavior on your Baker domain, okay? One geometry, they are all disks. Different dynamical behaviors, different normal forms which are conjugated to. And let me mention that there are several techniques to construct Baker domains, and the very standard one is also the one that mentioned Lasserempe yesterday, is that you start with a linear map on a set you want, and then you perturb it, or you use quasi-conformal surgery, or you use some other techniques to preserve your linear behavior on a certain set and construct the other properties that you want. Another great technique to construct Baker domains is lifting of parabolic and attracting basins. This is, for example, done in the paper by Fatou and Henriksen, but and is another powerful technique. So, what is the classification of Fatou components for transcendental functions in C? It's basically the same as in the polynomial case, with two new features. The first feature is that you have these Baker domains, which on their own have their own sub-classification into different dynamical types. The second thing is that your Fatou components are still disks, but instead of being bounded, like in the polynomial case, they can become unbounded. So these are a few images. This last picture is taken from the paper by Fatou and Henriksen. This I downloaded from the internet, so I don't know whom to thank. And the other ones, so this is an attracting basin. This is a parabolic basin, and you see here, these are the parabolic points, and they become really difficult to draw. So in fact, you should imagine this race to merge at this central point. This is a Siegel disk, and this is a Baker domain on which everything converges to infinity on the left. So let me change my plan, and let me make a break, take a 10-minute break here before we look at automorphisms of C2.
Okay.
So we start at 11:10. I don't know. Is that okay? It's 7 minutes. I don't know if it's okay.
Fine. Okay. So it's 3 past.
And I'm so sorry, I'm not in Barcelona, as you all know, but we will catch up. And since we are all fresh, we are ready for C2. So let us look at our automorphisms of C2. We have two worlds, polynomial and transcendental, okay? Henon map, so the special thing, a function in one variable plus a linear perturbation and a swap in the second coordinate. So before we get into the core of the matter, let me point out that there are a couple of things that you should be paying attention to when you look at C2. The first thing is that it's useful to distinguish between cases in which the iterates, you have a Fatou component, okay? This is our setup. Now it's useful to distinguish the case in which you have orbits which accumulate in the inside of your component and the case in which the orbits converge to the boundary. of your component, okay? Then we will consider the special case in which they converge to the actual line at infinity, to the boundary of your space. But for now, we distinguish between Fatou components which are recurrent, if at least one point converges in the inside of your Fatou component, and non-recurrent when all orbits converge to the boundary of the component. And in fact, for Henon maps, is either every point converges to the inside or every point converges to the boundary, okay? But a priori, as far as I understand, this is not true. And of course, escaping Fatou components are a special case of non-recurrent components. Instead of converging just to the boundary of your manifold, you literally converge to the boundary of your space. Another thing you should really pay attention to when you are in C2 is the rank of the limit function. So we have our Fatou components. We know that every subsequence has a convergent subsequence, which converges to a function. This function is called limit function, okay? If you have a subsequence which converges to a function in your Fatou component, this is called the limit function. And limit functions, in one variable, they are functions from an open set in C to C. So they either converge to a constant or they are open maps. In C2, you either converge to a constant or you are locally an open map, or you converge, your image is going to be a one-dimensional manifold. Now, smoothness is another discussion, but basically you have Sartre's theorem, which tells you that you have generically good points. I mean, there is a long story, but basically you should think of either the image of your Fatou component is going to be a point, like for example, in parabolic or attracting basins, or the image of your Fatou component is going to be squeezed on a one-dimensional surface. Sorry, this is more one-dimensional. Or the image of your Fatou component is going to be an open set. Okay, so these are rank 0 case in which you converge to a point, rank 1 case in which you converge to a manifold. Again, smoothness is another thing to discuss, okay, here. I don't want to get into this, but you should imagine a one-dimensional object. And finally, you could be an open map. So you could basically, the image under this limit map of your manifold is going to be a two-dimensional object. And this is the same as looking at the rank of the differential of your limit function, okay? You look generically, this is going to have a certain dimension. So basically, your differential is a 2 by 2 matrix. If it's going to converge to, okay, you look at the rank of this matrix, and according to the rank of this matrix, this will tell you the dimension of your limit manifold in the various cases. So let us look again at Fatou components in C from the point of view of recurrence and rank of limit functions. Your attracting basin, you are recurrent because you converge inside, and your rank is 0 because you converge to a point. Parabolic basin, you are non-recurrent because you converge to a boundary, rank 0 because you converge to a point. Rotation domain, you can do a couple of computations. You see that your limit functions are rotations. So you converge to rank 1 limit functions. And you're recurrent because every orbit accumulates in the inside. Baker domains are all non-recurrent. In fact, they're all escaping, okay? And what is the rank? It's always 0, because if you converge to the boundary is a point, is the point at infinity, so the rank is always 0. Now, escaping Fatou components for polynomials, you don't have to read this theorem, okay? It's there for completeness, but basically, when you have polynomial Henon maps, you have one Fatou component, which is morally the attracting basin of a point on this famous line at infinity, and you understand its structure. Complicated, it's called solenoid. I don't understand it, but people understand it. So for polynomial Henon maps, there are no escaping Fatou component except for morally an attracting basin of infinity, exactly like for polynomials. While if you look at recurrent components, which are non-escape, sorry, if you look at recurrent components for polynomial Henon, there is a perfect classification. You're either an attracting basin. I'm going to show you a picture of this because from the theorem, it's a bit weird to understand what's happening. So you're either an attracting basin or you converge to kind of a rotation surface in your manifold. Every orbit squeezes down to this surface on which you have a rotation. And this rotation surface is either a disk or an annulus. We don't know yet if an annulus is possible, but it's not discarded yet. Eric Bedford has a lot of evidence that an annulus may indeed exist. Or you have a subsequence which converges to the identity, which is kind of reminiscent of a rotation, but there is no normal form like in one variable. Okay, I think they're still called single domains, but you don't really have a conjugation to a rotation as far as I understand. Now let me show you a picture. what happens in C2 for polynomial Henon maps. You either converge to a fixed point interior to your component, and it's interesting because in this case, the geometric structure is C2, okay? So when you go to look at geometric structure in C2, you have many more options. If you're on tracking basin, you are a C2. This is called Fatou domain. It's basically a copy of C2, which is contained inside another C2, another story from the point of view of geometry. But for us, we just have to consider the fact that this is basically a C2. Then recurrent, in which you are squeezed down to your rotation surface. In this case, you can show that you have a product structure on the component, if I understand correctly. Then you have your, I call them single domains, but these are those domains in which you have subsequences which converge to the identity. You don't have a true linearization like in one variable. And as far as I understand, we don't know how the geometry works. And finally, you have this escaping Fatou component in the polynomial case, which is this attracting basin for the point 1, 0, 0 on the line at infinity, and you understand its structure. Well, people understand its structure. What about non-recurrent Fatou component? You remember the ones for which the limit functions would go to the boundary. There is not much known, huh? There are no examples of non-recurrent Fatou components, except when they converge to a point. So rank 0 parabolic basin, they kind of exist in C2. And what is interesting is there are assumptions by Peters and Lubitsch and Peters, under which recurrent Fatou components with rank 1 limit function cannot exist. Okay, so non-recurrent Fatou components, sorry, I said it wrong. Non-recurrent Fatou components on which you converge to a point on the boundary is kind of the analog of parabolic basin. I'm not sure about their geometric structure in this case, exist, no problem. But to find non-recurrent Fatou components of rank 1, it's not known whether they can exist or not. And let me mention that morally speaking, the boundary of an open set in C2 is something which is real dimension 3. So it's not unthinkable. It actually seems to be kind of natural to think that you may have limit functions which converge to the boundary and will be some submanifold of complex dimension 1 inside this boundary in which you have a lot of space because you have R3. Okay, clearly the boundary is a fractal, it's not smooth. So this discussion is a bit unclear, but if they don't exist, there must be a good reason why they don't exist. So more generally, for general non-polynomial automorphism, there is no classification of recurrent, there is no classification of non-recurrent, it's very open. And there are examples of Fatou components which converge to a parabolic point. I call it parabolic point, but it's a bit sloppy in situ, okay, just so that we understand. So there are examples of Fatou components which converge to parabolic points on which are not simply connected, so they are biolomorphic to C times C star. There are examples and there are several examples of non-recurrent Fatou components in which you converge to a rank 1 limit manifold, okay? So for polynomials, we don't know if they can exist. For polynomials automorphisms, we don't know if you can have a non-recurrent Fatou component on which you converge to some complex dimension 1 manifold in the boundary. For more general transcendental automorphism, you can construct them such that you have Fatou components on which you have rank 1 limit functions in the boundary. However, they are not constant Jacobian, and they all have one specific dynamical behavior. I'm not going to get into this, but just to let you know that this example exists, Lilov and Jupiter, several works by Filippo Bracci with Bochthaler, Peters, Repicus. There are, except for Jupiter and Lilov, they are all very recent. They all have the same dynamical structure, and they don't have constant Jacobian. So for transcendental Henon maps, you can say much more, and you can actually classify recurrent Fatou components. The classification is the same for polynomials. Attracting basin, everything converges to a rotation manifold. Now you may have many more possibilities for the rotation manifold. It could be C or C star or D star. We don't know for sure. But still you can find the local product structure, and you can have this kind of single balls in which you have subsequences of the iterates which converge to identity, so clearly rank 1. Now, non-recurrent Fatou components, we don't know. it should be easy to construct parabolic domains. It should be easy to construct Fatou components in which you converge to a point on the boundary. We didn't do it, but I'm sure that somebody can sit there and do it. And it's not clear whether you can construct non-recurrent Fatou components in which you converge to a rank 1 limit manifold in the boundary. Not clear, okay? It may be easier than for polynomial Henon maps or not. So just to point out that this limit one, so this non-recurrent Fatou components in which you converge to the boundary to a limit manifold of dimension 1, really you converge to a complex curve, is not trivial to construct. However, if you're willing to look at escaping Fatou components, you can do it in a much easier way. So let us look at escaping Fatou components for these transcendental Henon maps from a more general perspective. You can construct several different types. Okay, one type is kind of the source type that you would expect, in which you construct an escaping Fatou components, really the analog of a Baker domain, in which you converge to a specific point on the line at infinity. So you have your invariant Fatou component, and all the iterates converge to a single point. Escaping, rank 0, because you converge to a point. And this may be the correct analog of Baker domains. And you have a nice linearization. And this we did a long time ago with Arosio, Fornes, and Peters. And another new example, which is and we have another new example of this escaping components, another type, which is interesting because in this case, you converge to the line at infinity, and the image of your limit maps is really all the line at infinity minus 2 points. So you can actually construct, so one variable, Baker domain, you go to infinity. Infinity is a point, or your limit function of rank 0. Several complex variables. You converge to the boundary. The boundary now is a complex line. It's actually biolomorphic to the Riemann sphere. Can you have Baker domains? I call Baker domains. It's not clear what the correct definition of Baker domains would be in several complex variables. So can you have Baker domains on which your limit functions are rank 1? Yes, you can. Okay. So I think I have about 10 minutes left. So let me tell you how you show that you can have Baker domains with rank 1 limit functions in C2. So another thing which is interesting is that, so you have seen, and I will not give a lot of details because it's worth spending time on these basic things. So let me remark that all other cases that we had until now for Fatou components for which we know the geometric structure, we usually have something like C times C or C times C star, and then we have this option in which you have a rotation surface times C, okay? These Baker domain are kind of a little bit of a different geometric structure because the Baker domain in which you convert to a point is biholomorphic to H times C, and the Baker domain in which you converge to the rank 1 limit function is biholomorphic to H times H. So this is a hyperbolic set from the point of view of geometry in several complex variables. So let me switch again to my writing. Theorem. And I will clearly not tell you a lot about the proof, but let me tell you what are the main steps. Take f of zw to be e to the minus z plus 2w comma z. What is this? This is a transcendental perturbation of the linear map that we saw right in the beginning of the talk. Swapping the coordinates, multiply 1 by 2, so that in the linear case, everything goes to infinity. Here we have the perturbation term, so everything will still go to infinity, where the perturbation term is small, and will do whatever she pleases in all the rest of the C2, okay? So this is our map. And the claim it has is that it has an invariant escaping Fatou component. Why am I not calling it Baker domain? Well, it's not even clear what the correct definition of Baker domain should be, okay? As an invariant escaping Fatou component U with exactly 2 distinct limit function. This is inherited by the fact that the linear map had two distinct limit functions. And what I think is interesting is that let's call them H1 and H2. They go from U, your Fatou component, to the line at infinity, the boundary of your manifold, and I have generic rank 1. Generic is necessary because of this smoothness business. And their image is exactly the line at infinity minus 2 points. So they're not only rank 1, okay? They're really the line at infinity minus the 2 antipodal points. This is not crucial for us. Just for curiosity, we can know exactly what it is. And F is conjugate to its linear part, which is what? The linear map, which sends ZW to 2WZ. The exact map that we saw in the very beginning. And finally, in this specific case, U is biolomorphic to H times H. Clearly, this is an example, okay? Like in many of these constructions in which you perturb a linear map, you have a lot of flexibility in perturbing. You can change your linear map. So like in many examples of Baker domains, this is kind of a stable construction. You can perturb it. But I'm just stating it like this for the purpose of the talk. So let me just tell you what are the steps of the proof. Observe that if you, so when is this perturbation term small? This is small if the real part of Z is large and positive, okay? So when does this map have a chance to have a Baker domain? When the real part of Z is very large. But then since you have a swap, you have some symmetry, so the real part of W should also be very big. So what are the steps of the proof? I'm gonna put some quotation marks. Step 1, show that the set in which both real parts are large, the set in which real Z, real W is bigger than, say, 2, is F invariant. Easy. And it's easy. I mean, you sit down and you do the computation. You calculate real part of the first coordinate of F of Z, real part of the first coordinate of F of W, and you can only see, and you can also see that if you have a point in this set W, its iterates, the norm of the iterates goes to infinity. I don't think I'm going to do the computation because we really have little time left. And I want to tell you a little bit about what comes in the proof. And then you do a computation, a recursive computation, and you can see that the even iterates and the odd iterates converge to limit functions H1 and H2 of rank 1 on your set W. So this is your C2, and you really consider the points in which real part of Z is bigger than something, real part of W is bigger than something. So I visualize it as a kind of quadrant, okay? And in this set, you can show convergence. Why? Because you remember the linear map. The even iterates. The linear map is the linear part of this function that we are considering, okay? The one that you will eventually be conjugated to. The linear map, the even iterates were converging to the function Z over W, and you can show that for your function, your true function with the perturbation term, they will converge to basically the same with some error term above and below, which is bounded uniformly on W. So this is really like a computation. This is some error term which is bounded. So once you get this, you get automatically that it's rank 1. Okay, you take Z and W who are very far apart in your W, you can do it because it's unbounded. The error terms cannot influence too much, so your image is really open. And the same for the odd iterates. So what do you have now? An invariant domain on which you converge to infinity, and you prove by computation that the limit maps are of rank 1, which means the image is an open set in this line at infinity. Step 3. Well, this is a parenthesis. You show that the image of your map contain the line at infinity minus these 2 points. Sorry, I'm writing it wrong. And then you show that there is a conjugacy. Sorry, I'm writing not very nicely. There exists a conjugacy between your F and its linear part on W, okay? And this is also kind of standard, and you use the same techniques that you use since Milnor's book for quadratic polynomials. How do you construct a conjugacy? One very basic technique is you iterate forward by your map, Fn, and iterate backwards by the linear map L to the n. If this converges, you will get a conjugacy for free, okay? So you consider phi n defined as L to the minus n composed with F to the n, and this converges to some phi, which is a conjugacy. And why do you converge? Well, again, because your error term is small, okay? So this is, again, a standard step. The last step, which I think is interesting, and in which, so this final example is a joint work with Alberto Saracco and Michela Zedda. And this last step, which I think is kind of the most interesting, is kind of based on some techniques that we have been using with Arosio, Farnes, and Peters in the other papers about Henon map. And it's based, so the last thing, what are you left to show? You would like to say that you can extend the conjugacy to all of your Fatou component, and get the complex structure. Of course, so what is the picture now? The complex structure of the Fatou component. What do we know now? We have our forward invariant domain W. Real part of both coordinates is very big, okay? And we have a conjugacy to some set phi of W. On your W, you have big F, which is acting, and on your phi of W, you have the linear map, which is acting. Now, if you take pre-images, if you take a union over n of F to the minus n of W, this is an automorphism, okay? You don't bump into critical points which break your conjugacy and transform it into a semi-conjugacy. This is really an automorphism. So you can extend your conjugacy to all of the pre-images of your W and get a conjugacy on all of the pre-images. And this will give a conjugacy to the pre-images under the linear map of your phi of W. This is a conjugacy, it's a biholomorphism. So what you get now is that you're conjugate on all the pre-images of your domain, of your good domain, and this is a conjugate, this is really a biholomorphism which conjugates to the pre-images of your union of the pre-images. And you can show this, that this is H times H. Now the big question is your Fatou component equal to the pre-images? This is a union of F to the minus n of W. And to show this is the same as saying that W is an absorbing domain. And how do you do this? You use harmonic functions. And the maximum principle, no, this is not called the maximum, yes, the maximum principle for harmonic function that was mentioned by Phil Rippon in his talk yesterday morning. I'm obviously not going to do in details, but this is your set, this is your W, okay? I know it's supposed to be straighter. No, this is the union of the pre-images of W. And you take a point P here. What you show, well, the first thing to do is non-trivial, it's not completely trivial, is to show that this is really the picture. So your U is really much larger than your images of W, and you have enough boundary, okay? Because a priori, your U could be W union a point, like W could be a space in which you have some punctures, and your U could be everything. So the first thing to do is that you have enough boundary to play this trick, okay? And the second thing you do is you look at appropriate one-dimensional disks, and you find harmonic functions. You find a harmonic function which is exactly 0. This is not true, I'm cheating. But basically you find a harmonic, I'm cheating because I want to finish in time. So you find a harmonic function which is let me call it U, which is 0 on U, and which is very small in A. On the union of these preimages. And then you get a contradiction because this harmonic function computed in P is equal to the integral over the boundary of your disk. You need to choose your disk carefully of U of zeta in the zeta. So this is equal to the union over the piece of the boundary contained in U, which is 0, plus the integral over the piece of the boundary, which is contained, let me call this set A, which is negative. But P is in U minus A, so this should be equal to 0. So this kind of trick of finding harmonic functions which behave in, because, so the whole idea of this harmonic function is that you have a definite rate of amount at which you go to infinity if you are in W or any of its preimages. If you are in U, this kind of means that you cannot go to infinity at the same speed. So this allows you to construct these functions. And then you apply this maximum principle to deduce that such a point P in the boundary cannot exist. So this was, of course, a bit quick. And okay, I kind of was told that I was 3 minutes over time. In fact, I'm 7 minutes in advance. Sorry, I missed the time. So do you have questions? At this point, I'll just stop here and ask for questions.
Okay, Anna, thank you very much. So please